Hello, welcome back to our next video in the series on non-commutative geometry and non-associative non-unital extensions through naive class theory. And in this part, we're going to start covering universal enveloping algebras, differential operators on groups, particularly Lie groups, and Hopf-von Neumann algebras. So let's get started. We'll start off by considering a synopsis of our path towards differential operators on Lie groups. So first, we'll start by covering Lie groups and Lie algebras. Then we'll go on to cover the tensor algebras of Lie algebras as well as their universal enveloping algebras. That will be right before we go into invariant differential operators, Hopf algebras, and W-star algebras, also called von Neumann algebras. And here's a picture of Jules Henri Poincaré, who contributed vastly towards the study of universal enveloping algebras and differential operators on Lie groups. But then we'll cover Hopf-von Neumann algebras. We'll take the W-star algebra structure and merge it with the Hopf algebra to create a stronger algebra of invariant differential operators on Lie groups, for which its center generates what's called Casimir operators. And here's a picture of Heinz Hopf. So first, let's consider what a group actually is in general. A group, which we'll denote capital G, is any set for which the following four conditions hold. Number one, we must have algebraic closure. For all A and B that are elements of the group, their product is also an element of the group. Two, associativity. For all A, B, and C that are elements of the group, the product of A and B with C is equal to A with the product of B and C. Three, there is an existence of the identity element. There exists I, that's an element of G, such that for all A that are elements of G, I times A equals A times I equals A. It's a universal equation that holds for a group. Then there exists an inverse property. For all A that are elements of the group G, there exists another element B that's also an element of this group, such that A times B equals B times A equals the identity. So now let's consider Lie groups and Lie algebras. A Lie group, which we'll call this fancy G here, is a group that is simultaneously a differentiable manifold with a smooth group multiplication mu that maps us from G cross G to G, alongside an inverse that is also smooth. And in the prior presentation, we discussed how the tangent space at a point on a manifold is a fiber of a corresponding smooth fiber bundle. But since a Lie group is a type of manifold, we can also consider tangent spaces at points on a Lie group itself, which we can denote T sub x of G, that is the tangent space at a point x on the Lie group G. And something interesting happens here when we consider the point on the Lie group that acts as the identity element that we defined earlier through groups in general. The tangent space at this point of the Lie group is what's called a Lie algebra, small g, of the Lie group. So G equals the tangent space at the identity element of the Lie group. Objects in a Lie algebra generate the symmetries of the corresponding Lie group. And in general, a Lie algebra is a vector space over a commutative ring called a field K. For example, real numbers and complex numbers are examples of a field. And endowed upon those is a binary product called a Lie bracket that takes us from G cross G back to the Lie algebra. And it obeys the following properties for all elements inside the Lie algebra x, y, and z, and for all scalars alpha that are elements of that field. So if we take the Lie bracket with x in itself, we get back 0. But if we have a scalar constant we'll call alpha, then alpha acting on x with y inside of that Lie bracket is equal to alpha acting on the Lie bracket of x and y from the left, or the bracket of x and y with alpha acting on it from the right. When we combine these properties, we find the antisymmetric property of the Lie bracket, such as the bracket xy is equal to minus bracket yx. And while it may seem intuitive that we can derive this relationship just from the very first condition of the Lie bracket of x with itself going to 0, we really need to understand the nature of scalar multiplication here in order to make sense of what it means to have a negative sign in front of this Lie bracket. So both of these conditions here lead to the antisymmetric property, not just one of them. And then we have x plus y with z inside of the bracket is equal to the bracket of x and z plus the bracket of y with z. And then we have a property called the Jacobi identity, whereas we take the bracket of x with the bracket yz, plus the bracket of y with the bracket zx, plus the bracket of z with the bracket of xy, we get 0. And we can generate this Jacobi identity to provide analyticity over Lie groups and Lie algebras in the sense that it's cyclic. And so if we have x bracket yz, then we can take the y out of that bracket, move it up front, and then take the x and drag it to the end to get y, z, x. And the same thing happens again with z, drag that out of the Lie bracket, and then take y and throw that back into the very end to get z, x, y. So you can think of this Jacobi identity by being generated by a cyclic process for which the Lie brackets go to 0 under these three elements. Here's a list of important Lie groups and Lie algebras. For Lie groups, the first we'll start out with are the n-dimensional vector space of real numbers. It's an n-dimensional Euclidean vector space with addition defined over it. The same thing is true also for complex numbers. That's also a Lie group. And these form the abelian Lie groups under vector addition. They're also called the trivial Lie groups. In the three-dimensional case of the Euclidean vector space, R3, we have three-dimensional vectors, and under the operation of the cross product, this also forms a Lie group. We also have the circle group S1 being isomorphic to U1. This is to say that the circle group is isomorphic to the set of all complex numbers with absolute value of 1. Then we have the general linear group, which composes all invertible n by n matrices over the field K, as well as the special linear group, which are all of those matrices in GL and K, but with a determinant of 1 specifically. Then we have the orthogonal group that preserves a symmetric bilinear form, satisfying the fact that A transpose A must equal the identity. And then we have the special orthogonal group where it's that same thing, but we also have the determinant equaling 1 in particular. And then we have the unitary group. This preserves a Hermitian form. And then we have the special unitary group that preserves the Hermitian form but with a determinant of 1. But then we have the projective general linear group 2C, which is isomorphic to the projective special linear group 2C, where C is the complex numbers. And that's isomorphic to SO plus 3,1. In other words, the general linear group modulo scalar matrices is isomorphic to that same group with a determinant of 1, which is also isomorphic to the restricted Lorentz group for 4D Minkowski spacetime. And then we have the symplectic group. And this preserves a non-degenerate skew-symmetric bilinear form. And then we have the compact symplectic group of quaternionic n by n matrices. Then we have what's called the Poincaré group, ISO n1, for an n plus 1 dimensional spacetime. We can consider this as the canonical isometry group of an arbitrarily dimensional spacetime as long as there is specifically one dimension of time. And then we have spin n, which is the double cover of SON. So we can think of, for example, if you have a spinner in spin n, we see that it takes two 360-degree rotations in SON to correspond to a single rotation in spin n. That gives us the idea of what's called spin 1/2 or spinners. So spin n is a very good group to use for spinners. But then we also have the conformal group over a manifold M. And these contain basically all the transformations that preserve angles on a manifold. That's what the conformal group does. And so you could have something like ISO, say, 4-2, which would be the conformal group of a 5-dimensional anti-de Sitter spacetime. And that would be obeyed by, for example, the Maxwell equation in a vacuum. But then we have the exceptional Lie groups. For example, G2, which is essentially the automorphism group of the octonion algebra. And it's a 14-dimensional Lie group. And then we have F4, which is an isometry group of a 16-dimensional Riemannian manifold called the octonionic projective plane. And that's a 52-dimensional Lie group. Then we have E6, which is a 78-dimensional family of Lie groups, as well as a family of Lie groups that are E7-like that are 133-dimensional in general. The same goes for any E8-like Lie group, which is 248-dimensional in its completely free representation. But then we also have Lie algebras. An interesting thing about the n-dimensional Euclidean vector space with the addition operation, as well as the complex numbers with addition, is that they are equal to their own Lie algebras. And so the Lie groups of the n-dimensional Euclidean vector space with addition and the complex numbers are simultaneously Lie groups and Lie algebras. These are the most trivial examples that we can really think of here. But then we can also think of the quaternions with multiplication induced over them. Those are also a Lie algebra. But now we have the n by n matrices over the real numbers, as well as the n by n matrices over the complex numbers in general. And so these are basically all the vector spaces of n by n matrices with a Lie bracket between matrices A and B that equals A times B minus B times A. And then we'll have a bunch of Lie algebras here that more or less correspond to the Lie groups we see on the left, but they're just algebras instead of groups. They are the generators, also called the derivation algebras, of their corresponding Lie groups on the left. And then we have something called the Heisenberg algebra. And this is a central extension to the abelian Lie groups that we described earlier, such as the complex numbers with addition applied over them. But instead we also have this commutator between position momentum operators that's equal to I times the reduced Planck constant, h bar. And then we have an extension to that called the Schrödinger algebra, which includes the Heisenberg algebra, H sub n, but it also includes dilations and special conformal transformations for the Schrödinger equation itself. Going ahead of this, we have the Witt algebra, which is an infinite dimensional Lie algebra of derivations on Laurent polynomials. But then we have the infinite dimensional affine Lie algebras, such as the affine Kac-Moody algebra, which acts as a central extension to loop algebras over the Lie algebra G. And then we have a central extension to the Witt algebra itself called the Virasoro algebra. And corresponding to the Lie groups on the left, we also have exceptional Lie algebras here on the right. So that's G2, F4, E6, as well as E7, and then of course we have E8. Now let's consider tensor algebras of Lie algebras, as well as their universal enveloping algebras. Since Lie algebras play the role of generating various symmetries that we ought to be interested in for the development of a non-commutative geometry, it would be nice if we could consider somehow imposing a fully associative structure over them so that we can consider formal powers of elements within the Lie algebra. And this is precisely what a tensor algebra allows us to resolve. A tensor algebra, T of V, we'll call it, over a vector space endows that vector space with an associative non-commutative product called the tensor product, given by this O cross symbol. And it grades the vector space through the tensor product so that there exists a formal notion of powers of elements, if you will, called tensor powers, within that vector space. So T of V equals the direct sum from n equals 0 to infinity of the nth tensor power of the vector space V. We can expand this. V tensor power 0, direct summed with V tensor power 1, direct sum V tensor power 2, so on and so forth, up until infinity. And so that gives us the base field plus the vector space plus the tensor product of the vector space with itself plus the tensor product space of the vector space with the vector space with the vector space, so on and so forth. But since a Lie algebra is also a type of vector space, we can define its tensor algebra to be the following. We have the direct sum from n equals 0 to infinity of the nth tensor power of the Lie algebra G. And so T of G is equal to the base field plus G cross G, so on and so forth. This is called the free associative algebra generated by the vector space of the Lie algebra G. It's called free because we haven't imposed any particular conditions on the generators besides associativity and linearity. It might be ideal to impose some sort of grading on the tensor power so that we can do more with this algebra. We can do this by taking the quotient of this entire algebra by an ideal, which we'll call I, generated by a condition we desire. However, we do have to be careful when selecting our ideal in this case if we want to do something particularly useful with it. Because we want this to be defined in terms of the Lie bracket that's already available to us through the Lie algebra. And since products are defined here in terms of the tensor product, the most natural choice would be the ideal generated by the following condition for where tensor products and the Lie bracket go to 0 when you compose them. So we can have, for example, the ideal generated by x tensor y tensor x minus the Lie bracket of x and y. Imposing this condition for the ideal gives us a quotient algebra. But since the object inside our ideal goes to 0 within the quotient, we have a formal way of defining the Lie bracket in terms of the tensor product specifically. So x tensor y tensor x minus the Lie bracket of x and y is equal to 0, such that the difference of those tensors is equal to the Lie bracket. This unique quotient algebra is called the universal enveloping algebra. And x tensor y tensor x equaling the Lie bracket is a generalization of the canonical commutation relation in quantum mechanics. The Lie algebra g is a space of first-order left-invariant differential operators on the Lie group G, while the universal enveloping algebra is the space of all left-invariant differential operators of arbitrary order on the Lie group. But if we choose a basis of G in terms of x sub 1, x sub 2 up to x sub n, then an element of the universal enveloping algebra appears in the following form for each x sub I that themselves act as vector field derivatives. So all of these are elements of the universal enveloping algebra. And we can consider these as left-invariant vector fields that act as field derivatives. And the role of these vector field derivatives is to act, from the left, on elements inside the algebra of infinitely differentiable functions on the Lie group G. So the derivation in the direction x of f is equal to these vector field derivatives acting on the left on f, where the function f is an element of C infinity of G, the infinitely differentiable functions on the Lie group. And as a result, these operators commute with the left group action, which we call a pullback by a left translation. And this holds for any element h that's inside of the group G. This result remains valid for more general objects than just functions. For example, it holds in the case of covariant derivatives acting on sections of smooth vector bundles over Lie groups in the direction of left-invariant vector fields. Where this covariant derivative in the direction x is given by x upper I times the partial derivatives acting on s alpha plus the connection coefficients acting on s beta, then all acting on the basis vectors e sub alpha, where this gamma upper alpha sub I beta is the connection coefficient, and if I and beta are commutative and symmetric, then we have what's called the Christoffel symbols of the Levi-Civita connection. Another example is in the case of derivative operators that obey the Lie bracket, called Lie derivatives, that act upon differential forms over Lie groups in the direction of left-invariant vector fields as well. Where the Lie derivative of the vector field y equals the ith Lie bracket xy, and specifically the Lie derivative acting on the differential form omega equals the exterior derivative of the inner contraction of x with omega plus the inner contraction of x with the exterior derivative of omega. This is called the Cartan formula. If our construction involved the selection of right-invariant vector fields, we would have a similar situation in terms of right-invariant differential operators. If the Lie algebra structure is commutative, such that the Lie bracket goes to 0, we have the special case of bi-invariant vector fields. And in general, when we're talking about invariants here, we can imagine that if we were restricting ourselves to a coordinate basis discussion, we have what's called covariant derivatives. Now let's consider the opposite Lie algebras and Hopf algebras. Since we start off with left-invariant vector fields through the Lie algebra G, we say that the right-invariant vector fields are part of the opposite Lie algebra G op. We can then consider the universal enveloping algebras of both of these Lie algebras. So the universal algebra of the Lie algebra G is the algebra of all left-invariant differential operators on the group. Its opposite then is the algebra of all right-invariant differential operators on that group. The opposite algebra is essentially the same as the original algebra, except the multiplication on the vector fields is reversed. So A with the opposite product on B is equal to B times A. Both of these universal enveloping algebras are bi-algebras called Hopf algebras because their elements maintain the following properties for all x that are elements of G and all y that are elements of the opposite G. So delta x is equal to x tensored with the identity plus the identity tensored with x, where epsilon x goes to 0 and its antipode on x equals negative x. So epsilon x is called the co-unit, and S is called the antipode. So the same thing also holds for y, where the co-unit of y equals 0 and the antipode of y is equal to negative y. The space of all bi-invariant differential operators on the Lie group is located at the center of either of these Hopf algebras, such that the centers of both algebras are isomorphic. So the center of the universal enveloping algebra is isomorphic to the center of the opposite universal enveloping algebra. And the center of the universal enveloping algebra is the algebra of all bi-invariant differential operators on the Lie group. The problem we have here, though, is that we want to maintain the bi-invariant differential operators while gluing together the two Hopf algebras that we have constructed for left and right invariant differential operators. It's nice that we have this so far, though, because we can do a lot with this. The first step we might think of to glue together the Hopf algebras UG and UG op is to consider their tensor product. And this forms a tensor product algebra, an associative algebra. The problem, however, is that the co-products that are uniquely defined for each algebra conflict with each other to the extent that we lose a true center of this larger algebra. And when I say the co-product, I'm talking about that delta x and delta y's that we discussed on the last slide for G and G op. So consequently, while this is indeed an associative algebra of all left-invariant and right-invariant differential operators, we lose the bi-invariant differential operators. We lose bicovariance in the coordinate basis, for example. So their shared centers no longer appear to be centers from the perspective of this larger associative algebra. And this is because the center of the left Hopf algebra appears to act exclusively on the left, while yet the center of the right Hopf algebra appears to act exclusively on the right of that tensor product. And that kind of defeats the entire point of why we call it a center. We lose a true center of A here. So we can think of this algebra as operating on a Hilbert space, which is a space of square integrable functions on the Lie group in this specific instance, through left-invariant and right-invariant differential operators. And to preserve the bi-invariants with these left and right invariants, we can promote A to an operator algebra called a von Neumann algebra, also called a W star algebra. But there are a few things to cover before we're ready to do this. So now we'll cover W star algebras and Hopf-von Neumann algebras to close this up. A von Neumann algebra can be understood through the von Neumann bicommutant theorem. And it says the following. Let M be an algebra of bounded operators on a Hilbert space H. So we can think of like differential operators that normally would be unbounded on their own, but these things are intrinsically attached to the Hilbert space structure of H with the Lie group. And these bounded operators on the Hilbert space inside of this algebra contain an identity operator that is closed under the action of adjoints. So the closures of the algebra M must then be equal to the bicommutant of M. And that means that M is called a von Neumann algebra. So the bicommutant of M is basically the smallest von Neumann algebra containing the original operators of M, and it acts as, say, the commutant of M, denoted M double prime. And so if we have M prime, we have those elements that commute, and then with M double prime, we have the elements that commute with the elements that commute in M. Think of it that way. And as such, if we take the bicommutant of our tensor product algebra A, we obtain a von Neumann algebra that includes both the left and right invariant differential operators. But to maintain a Hopf structure, we obtain the coproduct in a weakly continuous way. So we can refine the antipode of a product as well and extend the co-unit as a normal state of the center of the algebra M. So the coproduct here maps us from M to a weak tensor product between M and itself. And then S, acting on the product A and B, the antipode acting on the product A and B, is equal to the antipode of B times the antipode of A for all A and B that are elements of this von Neumann algebra. And then the co-unit maps us from M to a base field in general. The collection M, delta, S, and epsilon is our complete Hopf-von Neumann algebra of all invariant differential operators, that being left, right, and center, where the center of M, denoted Z of M, contains all bi-invariant differential operators on the Lie group. And this gives us an operator algebraic perspective for which we can consider quantum group actions on non-commutative geometries. Since Hilbert space is referenced within our algebraic structure, we also obtain all bounded and unbounded varieties of these differential operators. And at last, we have a single algebra that unifies all invariant differential operators on the Lie group, their interactions, and a measure of their potential deformations under other group structures. And so finally, we acknowledge that the differential operators that act as elements of the center of this algebra, as well as the center of each unique universal enveloping algebra we discovered earlier via isomorphism, may indeed be familiar to those with the background in quantum mechanics. We call them the Casimir operators. They do not distinguish between acting on the left or the right. The commutativity is given by these. So the center of M is given by the left part of the von Neumann algebra intersected with the right portion. Their intersection of the left and right von Neumann algebras are your Casimir operators and generators of Casimir operators. And so the Casimir operator evaluated over the algebra M is equal to the Casimir operator tensored trivially with the identity, and that's the same thing as commuting that with one tensored the Casimir operator.